So, in the last lecture we ended with weak approximation theorem. This is a combination of Chinese remainder theorem and the fact that a number field when embedded in at all its Archimedean completion is the image of the number field is dense in that, and so we combined the two and the proof also combined the two. So, today we are going to look at arithmetic of local fields, and we will relate arithmetic of global fields with arithmetic of local field. So, the first problem that we are going to tackle is the following. It's a so we saw that if L over K is a finite extension of number fields and P is a non-zero prime ideal in K, non-zero prime ideal, then POL, the extension of P to OL, it is a product of some ideals because OL is a Dedekind domain, PI's are prime ideals, Pi not equal to Pj if I is not equal to j, and EI's are positive integers. Then question is, how do we find Pi's? So, given P and given this extension L over K, how do I find this factorization? I know that it exists. I also know a few more things about it. For example, the degree of L over K is summation EI Fi. So, there is some restriction on how many Pi's can there be, what the powers can be, etc. But how do I actually find them, or how do I at least find EI's and FI's to begin with? Okay, so what we are going to do is we are going to prove, we are going to find more or less find an algorithm to do this. It is not a complete algorithm the way I present it, but there are ways to get algorithms that give this in finite number of steps. We start with the following theorem. Okay, to this. So, this is the question that we are going to answer today, but we start with the following theorem. So, let the notation be as above. Then, if I take tensor product of L with Kp and I tensor product with over K, then this thing is isomorphic to LP1 direct sum LP2 direct sum LP3 all the way up to LPR. Okay. And this isomorphism is algebraic isomorphism and topological isomorphism. Both sides have some topology, both sides are direct sums of fields, and so they are algebras over Kp, and so as algebras and as topological space they are isomorphic. So, the first thing to look at, and this is tensor product over fields between fields. So, it is not a difficult thing at all. So, do not worry if you are not very good with tensor products. This tensor product has a very explicit description. So, let me tell you what the description is. So, how do we describe the tensor product? So, you fix a K basis E1, well E is probably a bad notation. So, maybe alpha 1 up to alpha n of L, then L over K, L tensored over K with Kp is a Kp vector space of dimension n, which is L over K, generated by, or maybe I should use the word spanned by, alpha 1 tensored 1 and so on up to alpha n tensored with 1. Okay. So, it is a very concrete thing. So, in particular, as I said here, n equals dimension n equals dimension over K p of L tensored K p, but this is also equal to dimension over K p of L p 1 direct sum L p r, right, as dimension of each of these L p i's over K p, this is E I F I, and summation E I F I is equal to n. Right. So, at least the two sides that we want to be isomorphic have the same dimension over K p. So, that is a good thing to begin with. If they had different dimension, we had no hope of proving they are isomorphic. Okay. Furthermore, there is a natural map from L tensored with K p over K. So, this to K, sorry, not K, L sub p I for each I. Right. There is a, how do you get a map from tensor product? Well, you get a map from a bilinear pairing from L cross K p, and then the universal property of tensor product will show you that there is a map from the tensor product, right. So, this is induced from L cross K p to L p I. So, alpha comma beta just goes to alpha beta. This is a bilinear pairing. Okay. And you can also write it directly in terms of tensor product, but here I am just telling you how to use the universal property of what tensor product is. Okay. And you put all these maps together. So, put all these maps together, which has an obvious meaning, to get L tensored K over K p to direct sum L p I going from 1 to R. Now, remember L, there is an injective map is a map from L to L tensored K p, right. What is this map? This is just alpha going to alpha tensored 1, and so we get L to direct sum I going from 1 to R L p I. Okay. And now, here is a maybe an exercise if it is not apparent to you. Weak approximation implies that image of L in L sub p I direct sum 1 to R is dense. Okay. Therefore, image of L tensored K p So, this is a map of vector spaces, right, and if a map of vector space is dense, image of a map of a linear map, linear function is dense for finite dimensional vector spaces, it has to be whole thing. So, image of this inside LPI is the whole space. Okay, i.e. the map is surjective. Is surjective, right, and now it is a map between finite dimensional vector spaces of same dimension, okay, by rank nullity formula. Injective as well, right. This is one of the most basic things you learn in linear algebra. And as this is a map of Kp vector spaces, it is also a topological isomorphism. Right. So, the topology also agrees because these are just finite dimensional Kp vector spaces and the topology is as a Kp vector space. All right. So, that is a very nice thing. You get that L tensored with Kp is just completion of L at all those primes. That is a very nice relationship we have. Okay. So, how do we use this? Let us see kind of halfway through what we want to do. Okay. So, again the notation is as above and let phi of x in Kpx be irreducible. Okay. Sorry, not Kpx. I want this to be in let me do this again. So, let phi, let me just start with something in phi x. I do not worry in Kx, I do not worry whether it is irreducible or not. I am not sure if I need irreducibility or not. So, I consider it phi of x in Kpx, right. Kp is a bigger field than K. So, even if phi is irreducible over K, it need not be reducible over Kp, right. And so, I can write phi of x is product I going from 1 to r of phi I of x, okay, where each phi I of x is irreducible in Kpx. So, I am taking a decomposition of phi into irreducibles over Kpx. Then degree of phi I, and there is a reason why I took I going from 1 to r, because this is what is going to happen, is EI up to reordering. I may need to reorder them if required, and phi I of x. Okay. So, now I know what I want for phi is the minimal polynomial of alpha over of alpha in Kpi over Kp, sorry, L, this should be L. Let me rewrite that whole thing. Okay. So, okay. So, here what is phi? So, L is k alpha and phi is the minimal polynomial of alpha over k. Okay, so that is what I start with. I start with a minimal polynomial of a generator of L over the base field k, and I want to see how it factorizes in kpx. And if I take a factorization into irreducible over kpx, then this is the relation that I have, that each of this factor is a minimal polynomial when you consider alpha as an element of LPI, right. So, just because minimal polynomial of alpha over k is phi does not mean that minimal polynomial of alpha over any other extension of k would also be phi, right. If you take square root of 2, then the minimal polynomial of that over q, minimal polynomial of square root 2 over q is x squared minus 2. But if you consider minimal polynomial of square root of 2 over the quadratic extension q square root of 2, then it is just x minus square root of 2, right, it is not x squared minus 2. So, similarly, what is the minimal polynomial of alpha will depend on which field you are asking minimal polynomial over, but there is an added subtlety here. If you can consider alpha as an element of LP1, LP2, LP3 and so on, and again the answer will depend on that, whether you are considering it as an element of LP1 or LP2 and so etc. Okay. So, so this could be confusing at first, like how can alpha have different minimal polynomials over the same field Kp, and the reason is that you consider alpha as an element of LP1 first, then as an element of LP2, and there is no comparison between LP1 and LP2, LP3 etc. Okay. So, remark right. So, minimal polynomial of alpha in LP1 over Kp is different from alpha in LP2, right, and so on. So, it is kind of a this is an added subtlety that you may not have seen before. Okay. So, how do I prove this? And of course, we use the previous theorem, but still okay. So, first of all, by the previous theorem, K alpha tensored with Kp is isomorphic to K alpha P1, K alpha P2 and so on up to K alpha PR, right. So, each, so L remember is K alpha. So, each LPI is generated by alpha over Kp, okay. In other words, LPI is equal to Kp alpha, okay. And again let me point out the subtlety. It seems that the right hand side does not depend on I, right. The left hand side, of course, LPI depends on I, which I you take, and it seems as if the notation suggests that the right hand side does not depend on I, but that is not true. It depends because you are taking alpha as an element of LPI, right. So, it is a it is a subtle point that you should get used to. Okay. So, what I am going to do now is I am going to let phi I tilde of x in Kpx be the minimal polynomial of alpha as an element of LPI, right. So, it clearly depends on I now. Therefore, degree of phi I tilde x, this is equal to EI Fi. Furthermore, we know that this is equal to 0 in LPI as well. Okay. It is phi of alpha is 0 in L and L sits inside LPI. Therefore, phi I tilde of x divides phi of x. So, now we know that each phi I tilde of x divides phi x, and we also know that phi I tilde is irreducible over Kp, K sub p. If phi 1 divide, if A1 divides B and A2 divides B, that does not necessarily mean that A1 multiplied by A2 divides B, right. We need some co-prime condition. So, we need that each of these phi I tildes they are pairwise co-prime, okay. And so, here is another sort of sophisticated point here, that the topology on LP1, LP2 and so on up to LPR are all different, right, because these are different places, as Pi is not equal to Pj for I not equal to j. So, this is something that we proved, that if you take the valuation on a local field, it is given by some, if you take the valuation on L, it is given by some prime, and the prime is uniquely determined. So, all these primes are different, therefore, the topologies, the valuations on them are inequivalent, and therefore, the topologies are different, right. So, that is one point, but the second point is that the topology on LPI is determined by topology on Kp and phi I tilde of x, right. So, why is that? Well, this is again a subtle point where we start L sub Pi is given by adjoining a root of phi I tilde, and so we want to extend the valuation on Kp to a valuation on L, this Kp alpha, where alpha is a root of phi I tilde, and so any element of that is a linear combination of phi I tilde with, right. So, since let me write it like this, this is isomorphic to Kp of x mod phi I tilde of x, right. So, it is a finite dimensional vector spaces with very specific relations coming from phi I tilde, and so you can extend the valuation that way. Therefore, phi I tilde of x is not equal to phi j tilde of x if I is not equal to j. Hence, phi I tilde of x and phi j tilde of x are co-prime if I is not equal to j. Okay. Therefore, product over phi I tilde of x I going from 1 to r divides phi x, right. But degree of this product is equal to summation EI Fi which is n, which is also equal to degree of phi of x, and they are all monic. Hence, phi of x is equal to product phi I tilde of x. Therefore, you cannot have two factorizations into irreducibles, right, for all I. This is after reordering if required. Okay, so that is how you prove this theorem, and so now it tells you something about how to find these how to find prime factorization, right, from. So what do we know now? Let me just recap what we know. So I want POL to be, so this is P1 to the E1 up to PR to the ER, right. So I want to find, so if we want to find EIs and FIs and R, then what we do is we consider L to be K alpha and find minimal polynomial of alpha over K, then find factorization of this minimal polynomial phi over K sub p. Okay. So, this gives us R, whatever R is, and then EI times FI. We get at least this much, right. We do not get EIs and FIs individually, but we have gotten R and we have gotten our EIs and FIs. So, to find EI and FI individually, we have to work a little bit more, and this we can't really do in general, but with some mild conditions on what primes we start with, we should be able to do this. So, this is by looking not just as prime factorization over Kp, but also over residue field. So, this is what we are going to do next time. Thank you.